We put men on the moon. We sent probes beyond Pluto, so far that a radio signal takes more than 20 hours to reach us back. We photographed black holes at distances so absurd that the light that reached us has been traveling since before the dinosaurs appeared. And yet, there is a place that humanity has never reached, cannot reach, and may never reach. That place is not in a distant galaxy. It is right beneath your feet. At this very moment, as you listen to me, less than 6,500 kilometers beneath the soles of your shoes, something is beating. Something that turns, that pulses, that generates colossal energy, and we don't even know exactly what it is. The heart of our own planet remains one of the deepest mysteries of science. And the word deep here is not a metaphor. What happens inside governs our world for billions of years. It is this invisible thing, buried under thousands of kilometers of rock and molten metal, that has protected every living being on Earth since life has existed. Without it, our atmosphere would have dispersed into space eons ago. Without it, the sun's radiation would have sterilized our planet well before the first fish appeared. Life itself, every tree, every bird, every human being, depends on this beating heart beneath our feet, and we have never seen it. Today we are going to descend. Not physically, because that is impossible, and we will explain precisely why, but mentally, layer by layer, we will cross our planet from the surface to its absolute center. We will meet the men who tried to crack this mystery and failed spectacularly. We will understand how scientists of the 20th century managed to see the interior of the Earth without ever touching it. We will discover what the depths of our world truly conceal, and why some of these discoveries have completely overturned everything we thought we knew. If this dive into the bowels of our planet fascinates you as much as it fascinates us, subscribe to the channel and leave us a like. That is what allows us to keep exploring the mysteries that mainstream science often leaves in the shadows. And tell us in the comments, from which city are you watching us right now, and what time is it where you are? Below the video, in the description, you will also find a link if you wish to support the channel's development with a donation. Every contribution helps us go further, search more, and bring you topics that no one else dares to tackle. Now, let's start going down. Let's take a moment to think about what that distance truly means. The surface of the moon is about 380,000 kilometers from here. That's far. So far that even light takes more than a second to make the trip. And yet, we went there. 12 men walked on that gray, dusty ground, picked up rocks, drove small electric vehicles through craters. We mapped the far side of the moon in detail. We probed its soil with seismic instruments, but the center of the Earth? It lies less than 7,000 kilometers beneath our feet. That is 60 times closer than the moon, and we have never been there, cannot go there, and have never recovered a single gram of material that came directly from it. Why this absurdity? Why does space, at distances that defy imagination, seem more accessible than the ground of our own planet? The answer comes down to two words: heat and pressure. Imagine pushing a needle into an orange. If the orange is 10 centimeters in diameter and you push the needle in 1 centimeter, you have penetrated 10% of the distance to the center. The deepest drilling ever accomplished by human beings, and we will return to this in detail, reached just over 12 kilometers in depth. On a planet whose radius exceeds 6,000 kilometers, that represents less than 0.2% of the way to the core, less than the mark of a pencil on the surface of that orange. That is how far we are from the goal, and the reasons are brutal. As you go deeper into the Earth's crust, the temperature rises, and it rises fast. At the depth reached by that record-breaking drill, rocks reach temperatures that would melt lead like butter under a summer sun. Drilling tools become useless. Materials soften, deform, collapse. The hardest metal we know how to make becomes as pliable as a heated candle, and we haven't even crossed the crust yet. The mantle, which begins where the crust ends, is an entirely different story. As for the core, the heart of molten metal, the temperatures there are comparable to the surface of the sun. No known material can withstand that. No conceivable machine could survive it. But human beings did not accept this impossibility without a fight. The history of deep drilling attempts is a long series of glorious defeats. The race downward was, in its own way, just as mad and as intense as the race to the stars. It all begins in the 1950s, in the heart of the Cold War. While the Americans and the Soviets are fighting for control of space, a handful of American geologists decide to launch a challenge of a different kind. Their goal? To reach the Mohorovičić discontinuity, the boundary between the Earth's crust and the mantle, named after the Croatian geophysicist who discovered it in 1909. This boundary, simply called the Moho, is found at varying depths depending on the location. But beneath the oceans, where the crust is much thinner, it lies only 7 or 8 kilometers below the seafloor. In theory, it was within reach. The project receives a name worthy of its ambition: Project Borehole. The idea is simple. Drill from a ship positioned above the Pacific Ocean, where the crust is thinnest. In 1961, for the first time in history, a team of engineers drills from a ship in deep water, passing through more than 150 meters of sediment and reaching the underlying basalt. It is an extraordinary technical feat. President Kennedy himself sends a message of congratulations. But the real objective, reaching the Moho, remains terribly far away. The project bogs down in disputes between rival scientific institutions. Costs explode, and in 1966, the United States Congress cuts the funding. Project Borehole is abandoned, and the mantle has still not been reached. The Soviets watch all this with interest. In the spirit of the Cold War, if the Americans failed to pierce the oceanic crust, the Soviet Union might succeed by going about it differently, by drilling from dry land. In 1970, on the Kola Peninsula in the far northwest of Russia, where birch forests meet the Arctic tundra, a team of Soviet scientists begins to dig, and they won't be stopping anytime soon. You have to understand what the Kola Peninsula represents to appreciate the improbable nature of this undertaking. It is a remote region, swept by polar winds, where winter lasts for months on end, and Arctic night erases the sun for weeks. It is there, in the middle of this frozen wasteland, that Soviet engineers will build one of the most extraordinary industrial structures ever erected by a human being. A massive drilling tower. Kilometers of steel rods, laboratories, analysis facilities, a scientific city conjured from nowhere, with the single mission of piercing our planet. For 20 years, engineers drill. The machine advances, sometimes quickly, sometimes very slowly. Accidents happen. Rods break at depths too great to retrieve them. Holes must be abandoned and restarted from an intermediate depth. In 1983, the drilling passes the 12-kilometer mark. It is then the deepest artificial point ever reached in human history. The site is unofficially renamed the deepest hole in the world, and in 1989, Borehole SG3 comes to a permanent stop at 12,262 meters. Why did it stop? The Cold War is ending, budgets are collapsing, but above all, the Earth won. At that depth, the temperature of the rocks had surpassed all predictions. The engineers perhaps expected 120 degrees. They found more than 200 degrees. The rock, under this combined heat and pressure, begins to behave like warm plastic. It closes back around the drill rods, deflects the trajectory, destroys the tools. Continuing was physically impossible with the available technology. In 1992, the project is officially halted. In 1995, the site is closed. Today, all that remains of this titanic endeavor is a welded metal cap on a hole 23 centimeters in diameter in the middle of the tundra. 23 centimeters, less than the width of a dinner plate. And after 20 years of effort, the depth reached represents barely a fifth of the distance to the Moho, the first major geological boundary. Not the mantle, not the core, not even the boundary between the crust and the next layer. The Earth held out, unmoved. But this drilling was not in vain, far from it. And this is where the story becomes fascinating, because the discoveries made at Kola were not at all what scientists expected. Let us recall what science believed it knew before Kola. Geophysicists had a theory about what lay at roughly 7 kilometers depth, a sharp transition between the granitic rocks of the upper crust and the basaltic rocks of the lower crust. This transition had even been detected indirectly through seismic waves, which appeared to change speed at that depth. It was a well-established scientific certainty, and Kola proved that certainty false. At 7 kilometers depth, there was no basalt. The researchers found only metamorphic granite, granitic rock transformed by millions of years of pressure and heat. The change in seismic wave speed, which everyone had interpreted as a transition in chemical composition between two rock types, was in reality something far more subtle, a change in the physical properties of the granite itself, made more plastic, more fractured, more porous by the extreme conditions. The distinction is not trivial. It means that our main tool for seeing inside the Earth, seismic waves, can mislead us if we don't know exactly how to interpret the signals. The second surprise was even more staggering. At more than 5 kilometers depth, in a region where no one would have expected to find water, geologists discovered that the rocks were saturated with liquid. Water was flowing freely through the rock at depths where pressure should have made this impossible. This water had not descended from the surface. It was trapped from millions, perhaps billions of years ago, formed by chemical reactions within the minerals themselves. Atoms of hydrogen and oxygen, released by pressure and heat, recombined into liquid water at the heart of the rock. It was water that no one had ever seen, a primordial water, born in the bowels of the planet. Third surprise? Life. At 7 kilometers depth, in rocks that had not seen light for billions of years, scientists found microfossils, the remains of 24 different species of unicellular marine microorganisms, preserved intact in the rock for more than 2 billion years. These fossils tell the story of an ancient sea that covered what is today the Kola Peninsula, long before the first complex animals existed. And this discovery also raised a dizzying question. If life can leave traces this deep, how far down can it go? Can rock still harbor microbial life at depths we haven't even come close to? Science has no definitive answer yet. Fourth discovery: gas. The drilling mud coming back up from the most extreme depths was described as bubbling, not with hot water, but with hydrogen gas, in large quantities, a concentration that was far from trivial and that raised questions about the chemical reactions occurring in the depths of the Earth's crust, where no laboratory has ever been able to conduct direct experiments. It is in this context that the legend of the well to hell was born. When the account of an alleged discovery began to circulate in the international press, a winged creature said to have burst from the hole, the screams of millions of the damned, recorded using a microphone lowered into the borehole, the world was gripped. The story was perfectly fabricated, a pastiche of a scientific article blending authentically sounding Russian names, credible geological terminology, and biblical horror. Today, it is established beyond any ambiguity that this story is entirely invented. The Kola borehole heard no screams. There is no cavern at 12 kilometers depth, and above all, at that depth, the temperatures would have instantly destroyed any recording equipment. But the legend says something true about us, as human beings. It tells us that when faced with the absolute unknown, with a bottomless hole in our own planet, our imagination prefers to fill that void with monsters rather than live with the emptiness of what we do not know. The reality, however, is far stranger, and it begins with a simple question. If we can't go down and look at what's happening inside the Earth, how can we know anything about it at all? The answer is that the Earth speaks. It doesn't speak often, and when it does, it's not with words. It speaks with tremors, and we have learned to listen. An earthquake is a catastrophe for those on the surface, but for a geophysicist, it is a free X-ray of the planet. Every earthquake sends waves in all directions, waves that travel through the entire planet, bounce off the boundaries between different geological layers, accelerate in dense materials, slow down in lighter or liquid materials, and eventually emerge at the surface on the other side of the globe, where ultra-sensitive instruments record them. It is as if you struck a bell, and the way the bell rings told you exactly what it was made of, layer by layer. Two types of waves are of particular interest. P waves, the first arrivals, the fastest, travel like sound through air. They compress and expand matter in their direction of travel. They can pass through anything, solid, liquid, gas. S waves, the secondary waves, move by making rock undulate sideways, like a shaken rope, and this is where their informative power lies. S waves cannot travel through a liquid. If they encounter a liquid layer, they stop. They disappear from seismograms, and their absence tells us something fundamental about what they have passed through. All of this we learned through a series of discoveries that unfolded over just under half a century, each one revealing an additional layer of the mystery. The first major breakthrough took place in 1909 in a Croatian city called Zagreb. Andrija Mohorovičić, a meteorologist turned geophysicist, analyzes seismograms of an earthquake that occurred several dozen kilometers to the south. He observes something troubling. The seismic waves arrive in pairs. There are two series of P waves, one after the other, as if the signal had taken two different paths. Mohorovičić spends weeks analyzing this data. His conclusion eventually imposes itself with absolute clarity. There exists, somewhere beneath his feet, a boundary, a limit between two types of rock of different densities. Direct waves travel through the shallower, slower rock, but other waves plunge deeper, encounter this boundary, bounce back, and return to the surface following a longer path, but at a greater speed, because the rock below is denser. By arriving first, despite their longer journey, they betray the existence of a sudden change in properties at a few dozen kilometers depth. This boundary now bears his name, the Mohorovičić discontinuity, or simply, the MOHO. It is the boundary between the crust and the mantle, and Mohorovičić never saw it. He deduced it, the same way a blind person understands the shape of an object by touching it. 3 years later, in 1912, a German geophysicist named Benno Gutenberg examines something different. He notices that for sufficiently distant earthquakes, there exists a zone on the surface of the globe where P waves do not appear at all, a seismic shadow zone, as he names it. This does not happen by accident. The waves have encountered a surface that strongly refracted them, deflecting their path. Gutenberg calculates that this surface lies approximately 2,900 kilometers underground, and he understands what this implies. At that depth, the nature of matter changes radically. The medium through which the waves are traveling shifts suddenly from solid to something else, something whose properties are incompatible with the propagation of S waves, which disappear precisely at this boundary. It is liquid. The Gutenberg discontinuity marks the boundary between the solid mantle and the liquid outer core. But the story doesn't stop there. In 1936, a Danish seismologist named Inge Lehmann makes one final discovery, and it is no small one. She observes, on the seismograms of major earthquakes, something that should not exist according to the model then in use. P waves that reappear in a zone where they should be absent. Waves that seem to have bounced off something inside the core itself. Lehmann spends months making calculations by hand. In an era without computers, armed with rulers and logarithm tables, and concludes that there must be a second boundary inside the core at around 5,150 kilometers depth. Below that boundary, the matter is solid again, a core within the core. The Lehmann discontinuity, and behind it, the inner core, the solid heart of our planet. Let's take a moment to think about what these three people accomplished. Mohorovičić, Gutenberg, Lehmann. None of them went down to dig. None of them recovered a sample of the layers they described. They reconstructed the internal structure of a planet from lines on paper. Vibrations recorded at the surface, translated into mathematics, transformed into a map of the invisible. It may be one of the most extraordinary intellectual undertakings in the history of science. And this map that seismology has given us is precise, detailed, and consistent. We know it so well today that we can travel mentally through the Earth, layer by layer, as if we had truly visited it. Let's start here, beneath your feet, wherever you are. The Earth's crust, the layer on which all known life rests, is thin on a geological scale. Under the continents, it is typically between 30 and 50 kilometers thick, sometimes more beneath great mountain ranges. Imagine an apple. The apple's skin represents roughly what the continental crust is relative to the rest of the planet. Beneath the oceans, this skin is even thinner, barely 7 or 8 kilometers thick. The continental crust is made mainly of granite and similar rocks, light-colored and relatively light in density. The oceanic crust is darker, denser, basalt, essentially. Together, they form the ground on which we build our cities, plant our trees, and bury our dead. The lower boundary of the crust is the Moho. That line, Andrija Mohorovičić discovered in Zagreb by listening to earthquakes. We still haven't reached it by drilling. It is there, a few dozen kilometers beneath our feet, and no human drill has ever scratched its edge. Below begins the mantle, and there, everyday intuitions become treacherous. The mantle is not liquid. The way S-waves travel through it proves this beyond any possible ambiguity. It is a solid, but it is a solid that behaves differently depending on the timescale at which you observe it. Over millennia, the mantle flows, not like water, not like lava, like extremely thick honey or glass subjected to persistent heat. This is what is called a viscous solid, or a fluid in geological terms. The material there is so compressed by the weight of the crust above it that it can seem rigid on the scale of a human life, but it deforms and flows over millions of years. It is this slow movement of the mantle that makes tectonic plates drift, raises mountains, and opens oceans. The upper mantle extends to about 670 kilometers depth. Beyond that begins the lower mantle, even denser, even more compressed, where minerals exist in crystalline forms that no surface laboratory can easily replicate. These two layers together make up more than 3/4 of the total volume of the Earth. The mantle is the dominant part of our planet, and yet it remains largely mysterious, because the only samples of deep mantle that sometimes reach the surface, carried by particular volcanoes called kimberlites, represent only a fragmentary glimpse of this immensity. At 2,900 kilometers depth, something changes radically. This is the Gutenberg discontinuity. S-waves stop. The silence in the seismograms says it all. We have just entered something liquid. Welcome to the outer core. The outer core is something no textbook illustration truly manages to convey. It is a sphere of molten metal more than 2,000 kilometers thick, a sea of liquid iron so vast that the entire moon could be lost in it. And this sea does not sleep. It is in perpetual motion, stirred by the heat rising from the center of the planet and by the Earth's own rotation, which imprints on these metallic flows a complex, swirling geometry. These movements are not chaotic. They are organized by precise physical forces, gravity, heat, the Coriolis force, into great vortices that coil around the planet's rotation axis, and it is precisely there that something extraordinary is born. Liquid iron is an excellent electrical conductor. When a conductor moves in a magnetic field, it generates an electric current. That current in turn generates a magnetic field. That magnetic field influences the conductor's movements. That modified conductor generates new currents, and so on, in a self-sustaining loop that has been running for billions of years. This is the geodynamo, the mechanism by which the movement of liquid iron in our outer core converts the planet's thermal and kinetic energy into a powerful magnetic field that envelops the entire Earth. This magnetic field, you cannot see it, cannot touch it, cannot feel it, and yet it is everywhere. It extends tens of thousands of kilometers into space, forming an invisible bubble around our planet. This bubble continuously deflects the charged particles streaming in from the sun, the solar wind, channeling them toward the poles, where they create the northern and southern lights. These auroras are beautiful, but behind their beauty lies a terrifying truth. Without the outer core and its moving liquid iron, without this geodynamo buried thousands of kilometers beneath our feet, the solar wind would not be deflected. It would strike the atmosphere head-on, It would strip away the lightest molecules, gradually evaporating our air into space. Our oceans would dry up. Our atmosphere would vanish. Life would go extinct. But that is not the only thing the outer core does. There is something at its center, something that even the most experienced seismologists took decades to accept. At 5,150 kilometers depth, at the very heart of the liquid core, something solid slumbers. And to understand what it is, you have to go even deeper, all the way to the absolute heart of our world. This inner core has a name, but before diving in, we must understand what the outer core does for us every passing second for billions of years. The outer core is the source of everything. It's liquid iron in perpetual motion, stirred by heat and set spinning by the Earth itself, generates colossal electric currents. Those currents produce magnetic fields. Those magnetic fields reinforce the currents, and together, they form a self-sustaining machine that has been running for billions of years, the Geodynamo, whose final product is the Earth's magnetic field that envelops and protects us from space. Let's think about what protecting from space actually means in concrete terms. The sun constantly emits a flow of charged particles, electrons, protons, nuclei torn from its atmosphere and hurled at terrifying speeds in all directions. This is what we call the solar wind. Without the Earth's magnetic field, this wind strikes the atmosphere directly. It doesn't tear the Earth apart, it is too diffuse for that, but it erodes. Slowly, inexorably, it captures light molecules from the upper atmosphere and carries them off into space. Over millions of years, the entire atmosphere evaporates. The oceans follow. Life disappears. We know this because we have seen it. It is exactly what happened to Mars. Mars once had a magnetic field. The traces are still readable in the ancient rocks of its surface, sequences of fossilized magnetization, like the imprints of a field that existed more than 4 billion years ago. But the Martian core cooled, progressively solidified, and the geodynamo went out. Without its magnetic shield, Mars lost its atmosphere. Today, the atmospheric pressure at its surface is less than 1/100th of what it is on Earth. Liquid water is impossible. Cosmic radiation bombards the ground without obstruction. Mars is a dead planet, not because it was too far from the sun, but because its heart stopped beating. Our heart, on the other hand, is still beating, but it has not always beaten the same way. And here is where the story of Earth's magnetic field takes an unsettling turn. Earth's magnetic field is not stable. It never has been. By analyzing volcanic rocks, which become magnetized in the direction of the ambient magnetic field when they cool, like fossilized compasses, geophysicists have reconstructed the history of our magnetic field over hundreds of millions of years. And what they discovered is troubling. The field reverses. Regularly, on geological timescales, the magnetic North Pole becomes the South Pole, and vice versa. This has happened about 300 times over the past 200 million years. The last reversal was approximately 770,000 years ago. We have therefore been living, for longer than the average, within a stable period. How does a reversal happen? It is not an instantaneous event. It is not that one morning the North becomes the South. It is a process that unfolds over thousands of years, sometimes tens of thousands of years. The magnetic field begins to disorganize. Its dipolar component, the great planetary compass oriented north-south, weakens. Secondary poles appear all over the surface of the globe. The magnetic field becomes a chaotic web, with zones of strength and weakness distributed in complex ways. And throughout this time, the overall intensity of the field diminishes drastically. At its lowest point, during the last major documented magnetic excursion, which occurred approximately 42,000 years ago, the intensity of the field had fallen to less than 1/10 of its current value. What happens at that point? The atmosphere is far less protected. Cosmic radiation penetrates more deeply. The solar particles that normally create auroras only at the poles begin to appear at much lower latitudes. Researchers have shown that during that episode, 42,000 years ago, measurable climate changes followed, an increase in ultraviolet radiation at the surface, a disruption of the ozone layer, significant meteorological disturbances. And it is no coincidence that this period corresponds to the disappearance of several large mammal species and the migration of certain human populations into caves, perhaps to shelter from a sky that had become dangerously active. This brings us to a very current question. The magnetic North Pole is moving. It has never been perfectly still. Sailors have known this for centuries, and navigation systems must regularly correct their charts accordingly. But over the past few decades, this movement has considerably accelerated. In 1970, the magnetic North Pole was moving at about 10 kilometers per year. Today, it is moving at more than 50 kilometers per year, racing towards Siberia at a pace that alarms specialists. At the same time, the average intensity of Earth's magnetic field has decreased by about 9% over the past 170 years, a trend measured and documented since the first systematic measurements of the 19th century. Is this a sign of an imminent reversal? Scientists answer, perhaps, but we are not in a position to confirm it. The dynamics of the outer core are chaotic by nature. Accelerations and decelerations of the field have occurred in the past without resulting in a reversal. What we know for certain is that the current intensity of the field is not the lowest recorded in geological history, and that if a reversal were to occur, it would take thousands of years, more than enough time for life to adapt. Life has done so hundreds of times. What might cause us more problems, however, is our technological infrastructure. Satellites, electrical grids, navigation systems, which were not designed to operate with a weakened or disoriented magnetic field. This is one of the reasons why space agencies and geophysical institutes continuously monitor variations in the field, with entire constellations of satellites dedicated to this task. Everything we have just described, this geodynamo, these reversals, this invisible protection, depends on a single actor, the liquid outer core. But there is something below. There is the inner core, and the inner core is solid, which is in itself a remarkable mystery. How did Inga Lehmann discover it? In 1936, this 48-year-old Danish seismologist was analyzing records of distant earthquakes at her Copenhagen office, equipped with a ruler, calculation tables, and impeccable mathematical rigor. She noticed something her colleagues had overlooked. Certain P waves were arriving in regions of the globe where they should not be able to reach. In the seismic shadow zone, that silent region identified by Gutenberg in 1912, where P waves vanish because they are refracted by the liquid core, weak but measurable waves were reappearing. The only consistent explanation, after months of calculations, was that there existed a solid sphere inside the liquid core. This sphere was reflecting and transmitting certain waves, allowing them to emerge in the shadow zone. Lehmann published her findings in a remarkably brief article, 3 pages, and they permanently changed our understanding of the Earth. The inner core, the seed, has a radius of approximately 1,220 kilometers. To give a sense of what that means, the Moon has a radius of approximately 1,737 kilometers. The inner core is therefore slightly smaller than the Moon, a solid metallic sphere roughly the size of our natural satellite, buried 6,000 kilometers beneath our feet, surrounded on all sides by the ocean of liquid iron of the outer core. Its composition is primarily iron and nickel, like the outer core, but in a purer, more crystalline form. The inner core has been growing slowly for billions of years by crystallization from the outer core. When the liquid iron in contact with the inner core reaches sufficiently extreme pressure conditions, it solidifies and incorporates into the inner core. This process releases lighter elements that rise back up into the liquid core, feeding the compositional convection that contributes to the geodynamo. The inner core thus grows at about a few tens of millimeters per year, an imperceptible rate on a human scale, but one that represents enormous quantities of metal over billions of years. The temperature at the heart of the inner core is close to that of the surface of the Sun, a heat absolutely inconceivable on the scale of our everyday experience. And yet, the iron is solid. The reason is counterintuitive, but physically rigorous. The melting point of a metal depends not only on temperature, but also on pressure. And the pressure at the center of the Earth is so colossal, several million times atmospheric pressure, that it keeps iron in a solid state despite a heat that, at ambient pressure, would turn it to gas. It is as if you were pressing so hard on a candle that even the most intense heat could not melt it. Pressure overrides heat, and the inner core remains solid. But this is where things become truly strange. The inner core does not simply sit there, solid and still. It does something that no one predicted. It rotates. And it does not rotate like the rest of the planet. This discovery was made by comparing identical earthquakes recorded at different times.
When an earthquake always occurs in the same location, what is called a repeating earthquake, the waves it sends through the planet should take exactly the same amount of time to cross the core, since they follow the same path. But the data shows that this crossing time changes slightly from one decade to the next. The only way to explain this variation is that the inner core has moved in the meantime, that it has rotated relative to the rest of the planet, and if it has rotated, it must be spinning at a different speed from the surface. For a long time, the data seemed to indicate that the inner core was in super rotation, that it was spinning slightly faster than the Earth's surface. Some models spoke of an advance of a fraction of a degree per year. That was already surprising. But in 2023, a study published in the journal Nature Geoscience triggered a real storm in the scientific community. Researchers from Peking University, after analyzing decades of seismic data, including data from Soviet nuclear tests of the 1970s, concluded that the inner core had practically ceased its superrotation around 2008, and that it had since appeared to rotate slightly more slowly than the surface. From the surface's perspective, the effect looks like a rotation in the opposite direction, but this is a reference frame illusion. The inner core continues to rotate in the same direction as the Earth, simply a little more slowly. It slowed down, then fell behind in relative terms. And this is where the study becomes fascinating. These researchers propose that this behavior is part of a regular cycle. The inner core oscillates. It accelerates, then decelerates, then accelerates again, over a period of approximately 70 years. A decade scale back and forth, like an enormous spinning top subjected to opposing forces. These forces are precisely those of the surrounding liquid outer core that drives it like a heartbeat, and the gravitational pulls exerted by the densest regions of the rocky mantle above. This cycle is not without visible consequences, even if they are minuscule. The length of a day on Earth varies very slightly, on the order of a few fractions of a millisecond, in phase with the oscillations of the inner core. This is not measurable by our watches, but the most precise instruments detect it. The rotation of the inner core is coupled to the rotation of the entire planet, and this internal dance leaves subtle imprints all the way to the surface. Other studies have added an even more troubling layer of complexity. Recent analyses suggest that the inner core is not homogeneous. It exhibits what seismologists call anisotropy. Seismic waves travel through it at different speeds, depending on direction. Waves traveling along the Earth's rotation axis cross the inner core faster than those traveling along its equator. This indicates that the iron crystals making up the inner core are not randomly oriented. They have an organized structure, aligned with the rotation axis, as if billions of years of convection and rotation had slowly oriented every iron crystal in the same direction, like trees in a forest bent by a persistent wind. And there is more. In 2023, another study brought additional evidence for something seismologists had suspected for about 20 years. There may exist a distinct structure within the inner core itself, a sub-inner core, a core within the core within the core, showing slightly different properties from the outer part of the inner core. Seismic velocities within it would be different, and the anisotropy there would be oriented in a slightly different direction. The origin of this structure would be fossil, the imprint of a cosmic event that occurred perhaps several 100 million years ago, a major impact or a period of disruption in the convective movements of the core, which left a scar in the very structure of the solid iron at the center of the planet. If this sub-inner core is confirmed, our textbooks will need to be revised. The Earth would no longer be a 4-layer planet, but a 5-layer one. The crust, the mantle, the outer core, the inner core, and the sub-inner core at the absolute center.
each layer revealing a page of an increasingly ancient history, ever more deeply buried. To understand why all of this exists, why the Earth has a core at all, and why this core is so enormous relative to the rest of the planet, we must go back even further in time. We must go to the birth of the Earth itself. Approximately 4,600,000,000 years ago, there was no Earth.
There was only a cloud of gas and dust turning around a young star, our Sun, in the warmth of its first nuclear reactions. In that cloud were considerable quantities of heavy elements: iron, nickel, silicon, oxygen. These dusts clumped together. Small blocks became larger blocks. Larger blocks became planetesimals. Planetesimals collided, merged, grew. The proto-Earth formed over a few tens of millions of years, a long duration on a human scale, but ephemeral on a cosmic one. At the very beginning of this formation, iron was distributed relatively uniformly throughout the mass of the protoplanet. There was no distinct core yet, just a ball of mixed rock and metal, subjected to constant impacts that released enormous quantities of heat. This heat melted a large part of the planet, and that is when physics took control. Iron is much denser than rock. In a molten material, denser substances sink under the effect of gravity, exactly as grains of sand settle to the bottom of a glass of murky water. Molten iron began to percolate downward through the partially molten silicate rocks, flowing toward the center of the planet like countless small streams of liquid metal finding their way to the lowest point. This process, called planetary differentiation, accelerated and completed itself in less than 1,000,000 years. In geological terms, it was instantaneous. The proto-Earth differentiated into layers. Iron and nickel sank toward the center, lighter silicates rose up. Within a few million years, a distinct metallic core already existed at the heart of the planet. Then came the most violent event in Earth's history. About 4,500,000,000 years ago, shortly after differentiation, the proto-Earth collided with a protoplanet that scientists have named Theia, a body roughly the size of Mars. This was not a glancing blow. It was a near head-on encounter at a fantastic speed. The impact was so violent that the outer shells of both bodies were partially vaporized. A colossal quantity of material was ejected into space, mainly light mantle rocks, little iron, because the metallic cores of the two bodies merged and sank to the center. This cloud of debris in orbit around the molten Earth condensed over a few tens or hundreds of years to form the Moon. This impact had enormous consequences for Earth's core. The merging of the two cores, that of the proto-Earth and that of Theia, amplified the core, heated it, made it even more active. The kinetic energy of the impact was converted into heat. The surface of the Earth remained entirely molten for millennia. And through all this melting, the core began to cool slowly, not from the outside, but from the inside outward, because heat rose toward the surface by convection. It is this slow, progressive cooling that billions of years later would give birth to the solid inner core at the heart of the liquid core. The Earth without a core would not be the Earth. This is the reality we grasp when we look at Mars, or when we look at the Moon. Our satellite is a ball of rock that cooled and solidified much faster than Earth because it is far smaller. Its core, if any active remnant exists, is minuscule. There has been no lunar geodynamo for billions of years. No global magnetic field, no protection against the solar wind, no active tectonics, no significant volcanism. The Moon is geologically dead, a petrified archive of the early days of the solar system. And it is precisely because it is dead that it is so valuable to science. It has preserved conditions that the Earth has long since erased. The Earth, for its part, has remained alive. And it has done so, in part, because it has a core large enough and hot enough to sustain its convective activity over billions of years. But why is this core still so hot after all this time? This is where an actor we have not yet mentioned enters the scene. The internal heat of the Earth comes from two main sources, and their respective proportions are still debated. The first is primordial heat.
the energy accumulated during the planet's formation, stored in the very mass of our world for 4,600,000,000 years. When planetesimals collided to form the Earth, their kinetic energy was converted into heat. The Theia impact added an enormous additional amount of thermal energy. This heat is still there, trapped in the depths of the planet, escaping toward the surface so slowly that we will never feel it at the surface. Barely a few tens of milliwatts per square meter, less than a low-power light bulb to cover an entire apartment. The second source is radioactivity.
The Earth contains significant quantities of naturally occurring radioactive elements: uranium, thorium, potassium in their unstable variants, which decay slowly and release heat in the process. This radioactive decay constitutes the majority of the internal heat produced today. Estimates suggest it represents between half and 4/5 of the total geothermal flux that the Earth expels at the surface. It is an energy source that declines very slowly over time, as radioactive nuclei transmute into stable elements. In billions of years, when much of this uranium and thorium has transformed into lead and helium, the Earth will be cooler, its core less active, its geodynamo weakened. The third contributor, more modest but real, is the heat released by the continuous crystallization of the inner core. Every time a quantity of liquid iron solidifies at the surface of the inner core, an energy, the latent heat of crystallization, is released. This process feeds the convective movements in the outer core and directly contributes to keeping the geodynamo active. The inner core is therefore both the product of the core's cooling and one of the drivers that allows this core to remain dynamic. A remarkable loop of interdependence. All of this translates, at the surface, into a discrete but measurable geothermal flux. Heat exits the Earth continuously, through mid-ocean ridges, where plates move apart and allow mantle material to rise, through volcanoes, which spectacularly expel a minuscule fraction of this total heat, through the ground itself, everywhere on the planet, so imperceptibly that only very sensitive instruments can detect it. Iceland builds power plants on this heat. Some European cities heat their buildings using deep aquifers kept warm by mantle heat. Behind every geyser, every hot spring, every volcanic eruption, there is the same thing: the heat of a core that is not yet finished radiating the energy of its own birth. But here is what is both fascinating and vertiginous. We observe all this without ever being able to touch it directly. Everything we have just described, the solid inner core, the geodynamo, the radioactive heat, the secular cooling, we know through indirect evidence, surface measurements, calculations, models. We have never recovered a single gram of material from the core. We have never observed it, other than through the vibrations it transmits. And yet, sometimes, something comes back up, something the Earth formed in its deepest bowels and expelled all the way to our surface, delivering messages in stone from the most inaccessible depths. These messengers the Earth sends us have a name that everyone knows, but that almost no one perceives for what they truly are: open windows onto the entrails of our planet. They are diamonds. A diamond is not simply crystallized carbon. It is a time capsule, a hermetically sealed natural vault that the Earth forged in its depths and expelled to our surface at a vertiginous speed, so fast that nothing inside had time to transform or alter. When you hold a diamond between your fingers, you are touching something that may have formed 2 billion years ago, 150 kilometers beneath the surface of the Earth, under conditions that nothing on Earth can reproduce. And in some cases, that diamond has traveled an even longer journey, from depths that are even more extreme. How do diamonds reach the surface? The mechanism is brutal and spectacular. In certain locations on Earth, generally above very old continental cores called cratons, the most stable and ancient parts of the crust, a particular column of magma rises from the depths of the mantle with exceptional speed. This magma, called kimberlite, rises through the rock at a speed geologists estimate to be greater than the speed of sound. It pierces the crust like a projectile, carrying with it everything it tore loose along the way: fragments of mantle peridotite, mineral crystals formed at hundreds of kilometers depth, and sometimes diamonds. This extremely rapid ascent is precisely what preserves the diamonds. If they rose more slowly, the progressive decompression and temperature drop would transform them into graphite, ordinary carbon, like the contents of a pencil. But kimberlite gives them no time to change. These kimberlite pipes are rare. Out of thousands known worldwide, only a few dozen are rich enough in diamonds to be economically mined. But for science, each pipe is a treasure of a different kind. The mantle fragments that kimberlite brings up, the xenoliths, allow geologists to hold in their hands material that has never been less than 100 kilometers from the surface.
Mantle rock from the upper mantle, in a laboratory. It is as if the Earth were sending up its own samples for us. But diamonds themselves are even more revealing, precisely because of what they contain. The mineral inclusions trapped inside a diamond are direct witnesses to the conditions that prevailed at the time and place of its formation. They have never interacted with their environment since the diamond captured them. The diamond is so hard, so impermeable, that nothing can enter or exit. To analyze the inclusions of a diamond is to read the petrified memory of an inaccessible place at a time we will never see again. What these inclusions have revealed is extraordinary. Garnets that can only form at precise temperatures and pressures have allowed the exact depth of formation of certain diamonds to be calculated. Traces of water trapped in minerals with a particular structure have shown that the mantle, which was thought to be essentially dry, actually contains vast reservoirs of water dissolved in its rocks, perhaps as much as in all our oceans combined. An exceptional diamond, extracted from a mine in Botswana, contained ringwoodite, a mineral that exists only in the transition zone between the upper and lower mantle, between 410 and 660 kilometers depth. And this ringwoodite was charged with water, direct proof that considerable quantities of water are found at depths that no one imagined to be hydrically active. Some diamonds go even further in their message. Researchers have found, in a few exceptional specimens, inclusions of minerals that do not exist under any surface conditions on Earth. Bridgmanite, ferropericlase, minerals that only form beyond 660 kilometers depth in the lower mantle. These so-called super-deep diamonds are extraordinary travelers, formed or trapped in regions that seismology describes, but that nothing human has ever approached. They have traveled all the way up through the lower mantle, through the transition zone, then through the upper mantle, before being carried up to us in a torrent of kimberlite. They are our only physical contact, our only tangible proof, with depths that we describe through equations and will never see any other way. This limit, seeing without touching, deducing without measuring directly, is one of the greatest frustrations of geophysics. And it is against this limit that some of the most inventive minds in current science are working to fight. Drilling, as we have seen, has run up against physical barriers that current technology cannot overcome. But drilling is not the only path imagined.
There is a more radical idea, bolder, crazier, an idea that has been circulating for a few years in circles of geophysicists and engineers, sending a probe that does not drill, but melts its way through. The idea is as follows. Rock resists drilling because the drills break, deform, become unusable at high temperatures, but rock melts. If a probe could be sent heated to a sufficiently high temperature, it would not drill through the rock, it would melt it ahead of itself and let it re-solidify behind, slowly progressing downward under its own weight. A probe melted into the rock, advancing like a drop of liquid metal descending through the planet. In theory, such a probe could descend indefinitely. As long as its heat source works, the rock parts before it and closes behind it. No need for holes, no need for rods, no need to extract cores. The probe descends, records, and data is sent back to the surface by signal. The obstacles are considerable. No material can remain structurally intact under the heat and pressure of the core. Even the most refractory metal melts well before reaching halfway. Communications with a probe at several thousand kilometers depth, through kilometers of dense rock, represent an engineering challenge for which there is currently no practical solution. And the probable slowness of the process, decades to descend a few tens of kilometers, makes the idea ambitious but difficult to fund or plan within any reasonable human timeframe.
The reality of exploring the Earth's core in the coming decades will likely look less like science fiction and more like particle physics. Neutrinos are particles so light and so weakly interacting that they pass through the entire Earth without encountering any obstacle. Hundreds of trillions pass through us every second without us feeling them. But at very high energies, neutrinos begin to interact slightly with matter, and this interaction depends on the density and composition of the medium they traverse. In theory, by measuring fluxes of high-energy neutrinos that have passed through the Earth in different directions, one can reconstruct a map of its internal density, a neutrino tomography of the entire planet, without drilling a single hole, without sending a single probe. The new Earth Probe project of the Institute of Earth Physics in Paris is exploring precisely this approach, in collaboration with existing neutrino detectors. The Ice Cube detector, buried under the ice of Antarctica, and the future KM3 NET network at the bottom of the Mediterranean are capable of exploiting atmospheric neutrinos to probe the internal structure of our planet. Initial analyses show that this technique can already distinguish the core from the mantle with growing precision. It is not yet precise enough to map the fine details of the inner core or its internal layers, but it is a start, and precision will improve with each new generation of instruments. Another approach, more down-to-earth, is simply to make better use of what we already have: seismic waves. Modern seismographs have reached extraordinary sensitivity. A new generation of instruments, quantum seismometers, promises even finer measurements, capable of detecting variations in vibration imperceptible to any previous technology. Global networks of seismographs, recording thousands of earthquakes per year and cross-referencing their data, continuously refine our picture of the core. The contours of the inner core, the texture of its boundary with the outer core, the velocity anomalies that may betray as yet unidentified internal structures, all of this sharpens every year. We are seeing the heart of the Earth with better eyes, even if we still cannot touch it. So, how close are we? The honest answer is, we are very far from a physical visit, perhaps forever, but we are not far from understanding. The fundamental questions, exactly what composes the inner core, why its oscillation follows this 70-year cycle, what precisely the nature of the sub-inner core is, how exactly the geodynamo has maintained itself stably for more than 3 billion years. These questions are on their way to being answered, not by probes descending into the depths, but by human minds, decoding signals sent from depths that our bodies will never reach. This brings us to a question that geophysicists often avoid formulating too directly, because it has something uncomfortable about it. What would happen if the geodynamo stopped? Let us begin by being precise about what stopping means here. The geodynamo cannot stop all at once, like a light being switched off. The magnetic field would not vanish overnight. But if the convective movements in the outer core gradually ceased, if the liquid iron slowed down, lost its ability to sustain these self-reinforcing loops of electric current, the magnetic field would weaken over millennia, then over tens of millennia, and the consequences would accumulate slowly, but with implacable certainty. Without a magnetic field, the magnetosphere, that protective bubble extending tens of thousands of kilometers into space, would collapse. The solar wind, those charged particles flowing constantly from the sun, would strike the upper atmosphere directly. Light molecules would begin to escape into space. Hydrogen would leave first. It is the lightest molecule, the easiest to strip away. Then helium. Over millions of years, atmospheric water dissociates under the action of unfiltered ultraviolet radiation, and the freed hydrogen evaporates into space. Without water, without a dense atmosphere, surface life becomes impossible. Cosmic radiation, no longer deflected, bombards the ground with an intensity that destroys complex molecules and progressively sterilizes the surface layers. We know the scenario is real because we can read it on Mars. Mars had a powerful magnetic field more than 4 billion years ago. Its oldest rocks preserve its imprint. Then, its core ceased to be active. The Martian geodynamo went out, and since then, Mars has been losing its atmosphere at a rate of a few tens of grams per second, carried away by the solar wind. What remains of its atmosphere is so thin that the surface pressure amounts to less than 1/100th of what we breathe. Water has disappeared from the oceans and lakes that once existed. The surface is sterilized by unfiltered ultraviolet radiation. This is not a sudden catastrophe. It is a slow, planetary extinction, written across billions of years of geology.
Why did Mars's core cool and solidify so early, while Earth's core remains active?
Because Mars is smaller, with a surface-to-volume ratio more favorable to rapid cooling. It lost its internal heat much faster. Its core, too small to sustain a geodynamo for billions of years, crystallized. The Earth is protected by its size, and by the particular composition of its core, which contains just enough light elements to sustain convection long enough for life to have had time to evolve all the way to us. So should we worry about Earth's core? The scientific answer is clear. No, not on any human timescale, nor even on the scale of the history of our species. Earth's core is still very active. The inner core is growing slowly. The geodynamo is robust. The variations in the magnetic field we observe today, its partial weakening, the movement of the North Pole, fall within the normal range of fluctuations documented over the past few million years. There may precede a reversal, or they may not. In either case, a reversal does not equate to an extinction. Life has survived hundreds of reversals. It would be disruptive to our technological infrastructure, but not fatal to the biosphere. What is certain, on the other hand, is that Earth's core will not last forever. In a few billion years, when the radioactive elements have been exhausted and the primordial heat has dissipated, the inner core will have taken over all the space of the liquid core. The geodynamo will go out. The Earth will become like Mars, like the Moon, a geologically dead planet, without a global magnetic field, without active tectonics. But that moment is so far in the future, farther than the current age of the planet, that the Sun itself will have become a red giant long before then. For now, the heart of the Earth is still beating, and it is this invisible heartbeat, buried at a depth we will never reach, that makes our world habitable.
This is what the center of the Earth conceals. Not a hell, not an abyss of fire, but something far more fascinating and far more indispensable. A solid inner core of iron and nickel, the size of the Moon, oscillating on a 70-year rhythm that we are only just beginning to decipher. An ocean of liquid metal in permanent convection that generates the magnetic shield without which life would not exist. A heat engine that has been running for 4 billion years, powered by radioactivity and the heat of our very planet's birth. And at the very bottom, perhaps, a sub-inner core, whose structure fossilizes a cosmic event hundreds of millions of years old, about which we still know almost nothing. We study it from the surface, through vibrations, neutrinos, diamonds brought up from the depths. We will never reach it physically. But we approach it intellectually, a little more each year, each recorded earthquake delivering one more fragment of an image that is not yet complete, and which, perhaps, will never be entirely so. That is the true mystery of the center of the Earth. Not that we cannot go there, but that even knowing everything we know, there remain, in this heart of iron and fire, questions that we do not yet know how to formulate. If this dive into the bowels of our planet has captivated you, if you want to keep exploring with us the mysteries that science leaves unresolved, black holes, the origins of life, the limits of the known universe, subscribe to the channel and leave us a like. Every subscription helps us dig even deeper. And in the description of this video, you will find a link to support us directly with a donation if you wish to contribute to the channel's development. Every gesture counts, and we are sincerely grateful for it. Tell us in the comments, from which city are you listening to us right now, and what time is it where you are? These details fascinate us almost as much as the heart of the Earth.